Hello class, I hope you're having a wonderful day. Today I would like to complete a practice problem from Chapter 8. It covers torque and force applied at an angle. So let's go ahead and get started. You have a 32.35 centimeter long wrench. You are tightening the mechanical assembly and the manufacturer requires a torque of 50 Newton meters and you can exert a force of 320 newtons. What is the greatest angle with respect to the vertical at which the force can be exerted? Now, one thing that I want to point out real quick here is we are going to calculate the greatest angle with respect to the vertical, okay? So, right here, I've got a picture here. Here's my picture of a wrench. And then we have our mechanical assembly, so we have a bolt or a nut right here. And you are going to apply a force at an angle here. And so we're going to have the axis of rotation, that's going to be the center of our mechanical assembly. And so let's go ahead and label that. This is the axis of rotation. Okay, now let's be specific about the angles that we're going to calculate here. The angle with respect to the x-axis, I'm going to label that with the Greek letter theta sub x. So this is the angle with respect to the x-axis. Next, I have theta sub y. So this is the angle with respect to the y-axis, okay? And here, I've drawn our perpendicular symbol. We have a 90-degree angle right here. And we know that whenever we apply a perpendicular force at a distance or at a lever arm, we're going to maximize our torque because we know that sine of 90 degrees is equal to 1. And so when we apply a perpendicular force, we maximize the torque. So what we need to do is label our lever arm. The lever arm is identified by lowercase r, and it tells us that our wrench is 32.35 centimeters. Now we know that we're going to have to quote this in units of meters, so we're going to perform some dimensional analysis here. We're going to multiply by 1 meter divided by 100 centimeters. Our units of centimeters will cancel, so this will give us 0.3235 meters. Okay, that is our lever arm. Now let's go ahead and write our base equation for torque. So torque is equal to our applied force times sine the angle theta. Now I'm going to be specific here because what we're doing is referencing the x-axis. So in our diagram, referencing the x-axis, we've identified this as theta sub x. So I want to do the same thing in my equation. And now we're going to multiply by the lever arm. Okay? So what I want to do is write down some knowns here. I'm going to create a column of knowns. The torque required by the manufacturer is 50 Newton meters. And the force that you can apply, identified by F sub A, is going to be 320 newtons. Okay? So, what we're going to do here is we are going to divide this up. We're first going to isolate sine theta sub x. Okay? So, we have our torque is equal to our applied force times sine of our angle theta sub x times our lever arm, okay? We're going to isolate sine theta sub x. We can do that by dividing by our applied force and our lever arm on both sides of the equal sign. So when I do that, I have F sub A times R, and we're going to do that to both sides of the equal sign. Boom, our applied force and our lever arm, those cancel. So this gives me sine theta sub x is equal to our torque divided by the product of our applied force and our lever arm. Now, we need to isolate theta sub x because we are trying to calculate this angle first here, okay? So what we're going to do is take the inverse of this function, and then this will give us theta sub x is equal to arc sine of our torque divided by our applied force times the lever arm. Okay, so this is the equation that we're going to use. I'll put a dotted box around this guy. Okay, so once again, theta sub x is equal to arc sine of the torque divided by the applied force and our lever arm. So at this point, let's just go ahead and plug in our values here, and then we will calculate the angle in degrees. So theta sub x is equal to arc sine, and in my numerator I have 50 Newton meters. Remember that torque is always described in units of Newton meters, and then applied force is 320 newtons times the lever arm of 0.3235 meters. Okay? So let's resolve the denominator first. I've got 320 times 0.3235 meters. So we'll continue this. I have arc sine 50 Newton meters divided by 103.52 Newton meters. Okay, so this looks good here because we know that our units need to cancel here because we're going to wind up with units of degrees over here. So in my numerator, Newton meters, in my denominator, Newton meters. That's great, those guys cancel. So here we have 50 divided by 103.52. And what we're going to do is take the arc sine of this numerical value. And so what I have is, I'll continue up here, I have arc sine of 0.48299985. I know that's very precise, but okay, that is the value that I have in my calculator here. Okay, now we're going to take arc sine of this value, and it's very important that you verify that your calculator is in degree mode, not radian mode. Make sure it's in degree mode. I've already verified that my calculator is in degree mode, so what I'm going to do is hit second function, and I have a TI-84, so this is how it works on mine. Second function, sine, and so when I hit shift, it puts it in arc sine, open parentheses. I'm going to use the answer stored in my calculator, and this is the numerical value here, close parentheses, and I get theta sub x is equal to 28.881 degrees. Okay? So what I want to do is I want to write that value down right here, 28.881 degrees. And remember that we have complementary angles here, okay? So the sum of these two angles, theta sub x and theta sub y, will be 90 degrees. So I've got theta sub x plus theta sub y is equal to 90 degrees. We need to calculate theta sub y. So what I'm going to do is plug in this value for theta sub x. I have 28.881 degrees plus theta sub y is equal to 90 degrees. So to isolate theta sub y, and remember this is going to be our maximum angle with respect to the y-axis, that we can apply a force to create a torque of 50 Newton meters. So we're going to do 90 degrees minus theta sub x, and this will give me 61.1185 degrees. So I'm going to identify this value up here, 61.1185 degrees. Okay? All right, so I'm running out of room here. I'm going to erase some of this. Now, what we need to do is verify that we have completed the problem correctly. Okay? So we know that our required torque is 50 Newton meters. So let's do this. We have required torque. We know this is 50 Newton meters, so I've got F sub A times sine theta sub x times our lever arm. So the force that you can apply is 320 newtons times sine of 28.881 degrees times our lever arm of 0.3235 meters. So let's grab our calculator here. I've got 320 sine 28.881. We're going to multiply that by our lever arm, 0.3235. And that gives me 49.999, and it keeps going, Newton meters. So this is perfect, all right? So we know that we completed the problem correctly. So our answer is this theta sub y of 61.1185 degrees. Now remember, it says the greatest angle with respect to the vertical, okay? So if we increase this angle, all right, so let's say we increase this angle to 70 degrees. Now we've got something like this. So that means if we're increasing the angle with respect to the y-axis, we're decreasing our angle with respect to the x-axis. And even if we apply 320 newtons at an angle that would be greater than 61.1185 degrees with respect to the y-axis, we would not be able to apply the correct torque identified by the manufacturer. Okay? All right? Well, I hope this problem has helped you today. If you have any questions, you can give me a call, you can send me an email, or contact me over Canvas. I hope you have a wonderful day.